First, I'll give a quick intro from the research perspective. And this is actually my second time at Berkeley. The first time I talked about this kind of things, learning from human feedback using a technique called marginal likelihood, which was actually developed here via my PhD advisor, Percy. It's actually an alternative to RL, but without the emphasis on exploration, and also because of the log, you have to do well on every single example. Yeah, anyways, we tried that, but without pre-training. More recently, okay. Yeah. So more recently, I was very interested in code LLMs. I thought, okay, yeah, they seem to be really impressive. Maybe a really good way to get to better AI. Kind of following, previously it was still language to programs. Now it's code LLMs. Did a bunch of work on that. And responsible for. Partly responsible for a bunch of benchmarks in the space. And most recently, I worked on Agentic RL on this code world model project that's recently released. Okay, but today I really want to talk about these benchmarks. So when you create, and actually, if I'm correct, this class had quite a few lectures about benchmark, intro to benchmark already. So I won't cover specific benchmarks. But when you make these benchmarks, it's all quite busy. There's considerations about oh, is this going to be effective? What's the quality, right? There's very little reflection on them. So this is what I want to talk about today. Okay, so back then you do a bit better, 10% better on ImageNet. It's a huge data set. Then there is no doubt that this works. What's happening now is that we have these more complex agentic benchmark. Well, I mean, human eval is no longer a complex benchmark, but it was a generative benchmark that takes a while to make and evaluate. And many papers report a relatively small improvement on them. And if you look at the traditional standards of statistical significance, many of the improvements are certainly not significant. Right? And if you look at the sizes, actually benchmarks are kind of getting harder but smaller. Right? So MNIST was 10,000, ImageNet 100,000. Before real generative benchmarks, the multiple choice ones like MLU 10,000. But once we get to these coding benchmarks, they go down to like human eval, which is one of the landmark benchmark in the area. Only 160 for examples. Others a little bit bigger. A few that I was partially responsible for, Crocs Eval, DS1000. We will try to, live code bench, we will try to shoot for about 1,000, but still quite a bit smaller than before. And now there are these even more complex agent evals, such as Sui Bench, various versions, Terminal Bench, which often needs hundreds of thousands of tokens and often hours, depends on how you run them. So these tend to be also in the hundreds. Okay, so one counterpoint then is each question now can be quite powerful and informative, right? So because you generate a lot of text or code or these agentic trajectories when you solve these problems. And that feels like it should be better than, say, true and false or multiple choice or classification questions, right? And I think we also have a certain intuition from humans, from all your experience being a student, right? So leading, I guess, intellectual contests have very few questions, but very long answers. So for instance, um, not sure why, yeah, but IMO, which the math Olympiad has 6 questions. The college version has 12 questions. And, yeah, and they have a range of difficulties. Okay, and I think it's also in the era now that if you solve a major open problem, you just have to solve one, right? And no one is going to say, oh, you only solved one problem. That's not statistically significant. And there are many of the more daily agentic tasks, which are more economically important, such as fixing issues, find bugs, vibe code, and I'm sure many in other domains. Okay, yeah. So here I pose a question. So what's the case? Are small benchmarks not reliable, even if they contain these hard, complex questions? Or B, can we somehow get more out of these complex questions? And we in fact should use these small but very hard benchmarks. Now, there are lots of benchmarks, lots of leaderboards, right? Some of these leaderboards really tell you exactly what the model did on each question. And otherwise, you can also run some kind of evaluation suite and get the individual performance. So in this attempt at exploratory data analysis, I have each dot on this plot is a question and the model. Actually, each column represents a model, and each row represents a question, and they are doubly sorted. So the models are placed at how well they do on average on a benchmark. That's the x-axis. We have the models on the. See the cursor? Yeah. Okay. You have the models on the left being the best models, and the model on the right being the worst models. And the questions are just sorted from the easiest question to the hardest question. So the y-axis is its rank. And the color is the accuracy of that model on this question. Okay, yeah, so we have this kind of data. You see there seems to be a clear trend of easy questions and hard questions, right? Good models and bad models, and a somewhat sharp transition, right? From this plot, right? So this was on Math 500 chain of thought. All right, and we can look at many benchmarks. I try to get a lot of it where there's data available, or I can run them. So some are a bit noisy. So then we have human eval on the left and BPP on the right. Right, maybe the division on human eval is less clear, but still clear on BPP. Sometimes you cannot get right. So the color gradient is because we have multiple draws for each question. Right, where yellow is like a 0.5, 50% probability of getting correct on that question. But sometimes these are external benchmarks that's aggregated by other people, and then we just get a binary correctness judgment. So a three-bench leaderboard is one of the most comprehensive with more than 100 model plus agent participating, and the live code bench on the right is another. I think lead author now, and it's also from Berkeley. Yeah, so even though they're binary, you can still see there are easy problems, hard problems, and some problems where no models solve. Okay, so one thing I can observe is there's just from this exploratory data analysis, there's a lot of inconsistency, right? So even though the model on the left is the best, right? But sometimes it fails on an easy problem, and some of the really rather bad models that succeed only maybe 20, 30 something percent of the time, but they succeed on some pretty hard problems. So this suggests to me that maybe the problems in these benchmarks are not that special, and even bad models have a chance of getting them correctly, um, even though maybe a lower chance. So back to the question I posed, right? Can we make up for low statistical power with hard problems? I think right. Certainly in some cases you can, but if you see this inconsistency, you should be pretty suspicious, right? So I'm trying to illustrate. Say you have a baseline model, right? Where okay, it's correct on some questions, and then you have if you had a strictly better model, right? That's better on more questions. Then maybe, okay, maybe some of these questions are really hard, really interesting, and somehow I got them right. That could mean a lot. But the reality seems more like the third line, where maybe you're a bit better overall, but or about the same overall, but you get some questions correctly, sometimes better, sometimes worse compared to the baseline. So so not always consistent. And I would maybe draw the analogy, right? Like if someone can write down if the right probably a very hard and long proof of p not equal to np, but they cannot define what np is or don't know some of the basic concepts, then maybe you suspect okay maybe they copied it somewhere. If it's truly open problems, they cannot copy it somewhere. But for the problems in the benchmarks, that could be possible. So that's the inconsistency. Another thing we can look at is um, really what is the probability that a model gets a question correctly, right? So so here is zooming in into the same kind of chart. Right. So here we have this question 1134 that only some very good models get consistently correctly, right? So slightly green here. But if we draw about 1,000 samples for each question, and some of the worst overall models still has a fair chance of getting them right? So in this case, that's the relevant number. You have still have 30% chance of getting it right. Some of the others are maybe less, 1%, 10%. Right? Depending on the case, actually, once you have some chance of getting the question correctly, making it more reliable may not be that impressive, right? So one could argue that actually the first percent is very important, right? So especially if you have a verifiable question where one way or another the verification is easier, maybe a proof or something. Then once you have a decent chance of getting it correctly, you can just try again and verify. And with a little bit of help, your model can actually increase the reliability without doing too much actual impressive things. Okay, so I think with that bit of exploratory data analysis, I I can convince you that at least for the benchmarks that we have, um, these small benchmarks are still not reliable, even if they seem to contain some hard and very hard agentic problems. Yeah. Okay, and to to give a more to give an example from daily life, once my kettle was broken, which is used to boil water, and like I took it apart, asked the model, okay, well, what happened? Can you help me identify what's the problem? Took a picture, asked well, what it is. It says, oh, there appears to be a robot. So I would trust its later advice a lot less, right? And I think it shows, yeah, well, hard problems may have many steps, and the probability of error will increase exponentially as the number of steps. So if you have some constant probability of error, then it's very unlikely that you can solve the hard problem. So there's some kind of a gradient, is what I'm trying to say here. Although sometimes you can jump over it, right? You can still get the answer correctly somehow, but you would trust it less. And as a result, so probably statistical analysis is still important now. And since we have some time, I want to try to convey the basics of how this works, especially maybe the concept of sampling from superpopulation, sampling from a superpopulation. In some sense, this is apparent from basic stats in textbooks, but this paper from Evan Miller articulated it pretty well in the context of LLM evaluations, which I think we linked for this class. So here I introduce a bit of a notation on to make the case of sampling, drawing multiple samples clear later. So which is a bit different from his notation. So first of all, we have so xi is a question. X is so it's the ith question. We have n total questions, and usually what an evaluation benchmark does is it takes the when it works on model A, it takes all the questions. AX returns, say, most commonly a 0 or 2, 0, 1 value, 0 for incorrect, 1 for correct. And we get the average A bar. So, right, and this is the particular set of n questions. But this estimation perspective says, well, actually, right, this we can draw other questions, all from the same distribution. And these n questions is just the particular representative. But we can use it to estimate the variance of the real population, right? And you can estimate with those n samples. And that's this variance of AX estimated by the empirical average on the samples. Yeah, and then because the mean is computed by averaging n things, there's the concept of the standard error of the mean, which is which is less than the variance of the population by the factor of square or 1 over square root n. It's giving you a pretty clear trend, multiplied by the cog. You can think of the variance A as fairly constant. Because so for instance, if it's 0, 0, 1 variable is the maximum, it can be 1 over 4, right? And often much smaller. So already you have an upper bound on how big your standard error of the mean is, without having any data. Okay, right? But that just gives you, if you draw repeated samples. If you draw other samples from the same population, what's the variance? of the mean. But actually, what we are more interested in is comparing model A and model B, right? And try to answer, did my maybe model B do better than model A? And this part is really for free, right? It's just better analysis. You already have all the data. So instead of asking what's the variance of A, you just ask, well, what's the variance of AX minus BX, right? So if you have a set of samples and there are 0, 1, now you have some set, it's either -1, 0, or 1 with some probability. And this could potentially have a large impact, right? So if A and B are almost perfectly correlated, then by doing this paired variance estimation, it could be potentially reduced to near 0. So that's a different version of variance. And once you have, which can also be normalized to be the standard error. And once you have the standard error, you compare it to how big the difference in mean is to get the z-score, right? And according to the theory, the z-score follows a standard normal distribution. So assuming your n is largish, which all of our evaluations still satisfy. So for instance, being one z-score away is quite likely to happen just by chance. By five since right, so yeah, five standard errors away is quite unlikely to happen, and the very conventional standard is about 2 standard errors away, which gives 5% chance of happening by chance. Okay, so that's how the basics of the statistical analysis works. And on this human eval data set, we have 164 examples, and typically your standard error will be about 4% for each individual component. If you don't pair them up, then to produce the 5% p-value, you need about a 10% difference in performance. Even with a paired test, you typically still need about 8%. And these are larger than what's reported by many papers. So I can also give a bit of intuition, right? So if we are considering unpaired, it's drawing from the distribution. So suppose A scored 50% on this year's exam, but B scored 60% on last year's exam. They contain different exact questions, but they are drawn from the same distribution. So that's unpaired. In the paired version, right, so in the unpaired version, B might have done better just because last year's was easier, for instance. But in the paired version, B also did the exact same exam as A with exactly the same questions, right? Then typically the 10% difference seems more significant. So basically, because they did the exact same problems, we can take advantage of it. Even though if you met the higher standard of unpaired, that also works. So one interesting thing about LLMs that I work out here is they can draw multiple independent samples. And especially with agent reasoning models, this is becoming more prominent. Yeah, and humans certainly can't do this. If I solve the problem, I cannot forget it and reattempt. So a common confusion is actually thinking that the only kind of noise coming from these evals is, oh, LLM gives you different predictions. But according to this theory, if you are sensitive to what exact questions are chosen, that's also a type of noise. in fact, could be the more important type of noise. Yeah, but we can develop a system to capture the setting as well, where you have in addition to the question variable x, we also have the noise variable epsilon, and your evaluations you average over both the questions and multiple draws of the model. Yeah, and you can estimate the variances as before, and now actually there's a decomposition of the total variance into first the variance due to choosing different questions, but averaging over the noise, and the noise due to sampling multiple times from the model. And actually, it's a nice identity that adds them up. Right, and you can as before get the standard error versions of them, and then apply the same z-scores in the now both the paired and with noise setting. So I don't need to do all the details here, but I try to work this out, correct to make sure they are correct, and to test it and run a bunch of empirical data, so maybe others can just use the results without fully understanding that and do it themselves. Yeah, so even though you have this ability, but sometimes it can lead to a bit of weirdness when you can say I can do this question correctly with probability 0.8. So here we can have in this example we have 8 questions, a model A and model B. So model A is overall not that great. It has a 10% chance of getting each question correctly. But model B has a 100% chance of getting the first 4 questions correctly, but 0 chance of getting the second 4 correctly. This can happen if you say do RL and maximize the expected reward. So your expected reward increased, but actually your the set of solvable questions decreased. And it's not completely clear which one is better, even though the average on average B is much better, right? So but if some of the errors can be corrected, say with a verifier in the loop, then A is actually better. Yeah, and all of these can be computed with a fairly simple, right, variance and mean estimations. There's more complexity with the correcting of bias. But one thing you don't have to do is you don't need to compute these with Bootstrap, which is a perfectly fine method. But sometimes when the answer is just like a p times 1 minus p, and they say, oh, let's compute this with Bootstrap, it shows a certain maybe lack of thinking, and we see a lot of examples of people doing Bootstrap incorrectly in the literature. Yeah, but actually, another reassuring thing is multiple very well established theories will give roughly the same answer. So, namely, Bootstrap is another viewpoint on this problem, where you say. Main idea is really if you draw resamples from the empirical distribution, that's the samples that you are actually given. It roughly behaves the same as drawing more samples from the unseen superpopulation. Yeah, and if you try to estimate that way, you get basically the same answer. Another quite classic method is sign test, treating this as testing a hypothesis, where the null hypothesis is where A and B is different, each have a 50% chance of being better. And it asks how likely is this random model to achieve an result as extreme as the one you observed. And this will also get about the same, give you the same result as long as A and B performance about not too far away from each other. Okay, so that's the method. Right. So I think the main contribution of this work is if I try to do this on all the benchmarks, all the model pair I have, right, carry out these different type of analysis, then maybe the numbers will be like fairly consistent, and you don't need to say, well, maybe my model pairs is very special and different from the others. So that's what I did. From try to do this on all model pairs and to take the average of take the average of all the meaningful standard errors, both paired and unpaired. Okay, and then I can write this down just for each data set. And one immediate observation then is that actually the paired test tend to return about the same result as the unpaired. Which means one way to interpret it is, okay, maybe their correlation is about 50%. Right. So if you actually apply the unpaired method, you would have to first multiply this by square root of 2, right, resulting in less power. But actually, if you do the paired, the standard error is about the same. So yeah, and the unpaired standard error you can more or less just calculate from the accuracy and the data set. So hopefully that makes it a lot easier. But there is a slightly weak dependence on the overall accuracy, right? So when your performance is near 0 or 1, there's the standard error is lower. Yeah, but it's not a super strong dependency. And yeah, but if you want to get this little bit of additional accuracy, I also gave the estimated standard error on each data set as a function of its overall accuracy. Right? So where here the green curve, the green dashed line is if I treat them all as independent. And the blue one is the prediction by another simple theory I will talk about. But first, we can look at a few examples of these. So for the most part, once your model has a reasonable performance on this data set, it follows this beta theory prediction. But when it's quite bad, then maybe it's more like independent. And this holds for almost all the data sets, and I see it very except with a few possible deviations. Right, one is here it's a MLU, it's a multiple choice test. So when all the models are really bad, right, like even your random model can get the 1/5 or 1/4. So there it was more like independent, but once the model gets better, it follows the beta prediction. Similar for live code bench. And also quite some and you also got the same result for bench with more data points, giving more confidence. And there's just one pair of outliers that I saw, and I digged into it a little bit, and there were this SWE fixer versus SWE fixer with a filter result. Yeah, where you got a strict improvement and thus much less standard error. I think yeah, it's a bit reassuring to say, okay, no, this is not some real universal phenomenon. It really only applies if you're testing LLMs, right? So even though these are a diverse set, somewhat yeah, somewhat diverse set of LLMs are trained by different people on different data, yeah, using different agents as well. But they are still all LLMs, and does seem to have similar noise behavior. Okay, so then I try to explain this a little. So why is it that it we get noise at that level? So one thing we can do is look at the empirical distribution of the probability uh, of getting correct for each tier of models, from really bad models to the best models. So here, this is the cumulative distribution function. Okay, and see what do they look like? And it turns out you can fit a beta distribution after accounting for the true real zeros. The questions where no model solve. And once your performance is good enough, the bimodalness, let's say, of the beta distribution increases, often with roughly the parameters summing to one, and that corresponds to the prediction that we showed before. Okay, so again, right, like if you use this model, then you can predict how much noise there is without having all the individual results. Yeah, and beta distribution is this the distribution on the interval 0 to 1, where in this range with I guess parameter summing to 1, they are bimodal. Whereas for parameter summing to be something bigger, it's more unimodal. Okay, so this also appears to fit multiple data sets. Here, MLU Pro chain of thought, and more discrete predictions like on sweep bench verified as well. Now, because now the empirical predictions are stepwise, because there's only so many models where we don't have multiple predictions, but the overall trend still seems to fit well. Okay, so that's what I wanted to say about measuring noise. There are other works such as run with multiple seeds, or something like measuring the variance of your training curve, which actually tend to lead to an underestimation. So after doing both the exploratory data analysis and some summary of it, right? We can in fact recommend this, right, in increasing accuracy, right? So if you really just want a ballpark figure, you know, just look at the table, right? It tells you what the standard error is by data set. And you don't need to do the additional work. To get a little bit more accuracy, you can look at you know, these charts, find okay, what's the range of your model, then read off that chart, right? Yeah, you can also provide your results on each question and use my code, right? Then runs all together, gives your particular comparisons in the context of all the other comparisons. So if you're getting something strange, you immediately know. Yeah, but you can also do your own tests and calculations, but it seems fairly error prone because there are several different types. Right. So noise is the thing that I think I took the furthest here, but there are a few other things you could do with this kind of data too. I think one kind of interesting one is you can say look at let's see if this works. Yeah, you can look at examples and see well, is this example correlated with a model, negatively correlated with the overall model performance? So the better the model is, the worse it does on this example. And we can find some such examples in many of the data sets. Right. But a lot of them are not actual errors, except on this on MBPP, where you have a bunch of negatively correlated examples that are actually either inconsistent or somehow incorrect. Yeah, but not all of them are mistakes. So this gives one way to audit the quality of the evaluation set. Yeah, we find a few mistakes in MBPP and which got incorporated into MBPP plus. You can also try to find suspicious models, actually, right? So once you say you have some suspect examples, where the leading model that say wasn't cheating will kind of overlook what's in the evaluation data set, but there may be a few model which gives the exact answer from the evaluation data set on this wrong example. So if there are a few of those, you can gather some evidence on what models maybe have trained on the evaluation data. Okay. Yeah, I think this is more for benchmark builder, right? So that was the absolute level of noise. But an important question is really how what kind of effect size can you measure with your benchmark, right? So this also depends on the standard error, but on many models when they release a series of models from small to large, right? So a place to get signal is then when you double your model size, how much improvement you get, right? Scaling law, which gives a consistent improvement. And you can ask, okay, so how on each benchmark, how much signal to noise ratio really also measured by z-score is there. And here you have still mostly just mostly a function of the size still, but occasional differences, right? So MLU can very reliably distinguish the next larger model, whereas many of the code evaluations like human eval cannot even distinguish doubling the model size. Yeah, I think around time. A few examples, but okay, but I think we can end here. So I give a way to look at all the question results, spend most of the effort characterizing how big the noise is, but also show a few ways to get some other information.